Last time we were solving questions related to physical cases of simple harmonic motion where some particles would oscillate because of the forces that are acting on it. Right? We saw a couple of cases of springs, some pendulums, and I think a couple of cases related to gravitation as well. Okay? Right? Therein we talked about both kinds of rotational motion, both kinds of oscillations possible. Some where the object would rotate and oscillate, and the other, like the last question that we did, was about translation. Okay, so now let's talk about one more case like this. Okay, so suppose a cylinder with cross sectional area A and length capital L floats over water. Okay, or actually any other liquid to do here, right? Not just water, or floats over liquid of density rho L. Okay. If the cylinder is given a small displacement downward and is released, so that it will perform simple harmonic motion and also find its type B. Okay, so let's draw what we are given here. There's just one thing that I forgot to mention here, is that density of cylinder, let's say density of cylinder is rho. Okay, density of cylinder is rho. So what's given is that there is some cylinder. It is having a cross sectional area A and length L, and it is floating over liquid of density rho L. Right? So let's say it's floating like hopefully you remember why anything floats. Which force acts on this so that it can float? Which force acts on it so that it can float? Yes, very good. The buoyant force, correct. It will act in upward direction, right? So let's say this is the drawing. This is the situation that we have in equilibrium position or mean position. Let's say this is the situation in mean position. All right. Okay. So now the question says that if you displace it little bit downward, let's say you push it from the upwards, okay, so it will go a little bit down, and then you release it, so it will jump up again. I'm sure you would have seen this kind of thing, right? If you put a rubber ball in water and then you press it, then it will start oscillating. Have you noted anything like that ever? Very good. Right. So let's say this is mean position. So in mean position, everything should be in equilibrium. Right? Everything should be in equilibrium. So if we draw every of this block here in mean position, the cylinder, not block, downward force mg, but mass is not given. Instead, density is given, area is given, and length is given. So density of cylinder rho into volume A into M. Clear so far? This is mass, and then multiplied by g. So this is mg. Right? Downward force mg. Upward force Fb. The buoyant force, right? Let's see how much would it be. we don't know how much is submerged, right? It's okay. It's not even necessary to know how much is submerged, right? But let's say in mean position, length x0, or let's say y0 actually, because this is in y-axis, I'm writing y. Okay, you can use x also, doesn't make any difference. So let's say in mean position a length y0 is submerged. Then do you remember formula of buoyant force, everyone? Do you remember formula of buoyant force? What's the formula of buoyant force? It is rho L, that is density of liquid into volume immersed into G, correct? Okay, everyone please revise old stuff, okay? Whatever we have learned so far will be used in other chapters as well. So rho L V immersed into G. How much is rho L? That's the density of liquid given in question, rho L, okay, no big deal about that, fine. Volume immersed. This much is the volume immersed. So that volume immersed is A into Y0. Clear? Volume immersed is A into Y0 and then into G. So this is the buoyant force. And now in mean position, remember we did this calculation for mean position, so that clearly means that in mean position you are going to get these two as equal. Okay, you are going to get FB and this as equal, right? Total force 0. So that's why we can say Y0 will be equal to rho upon rho L into capital L. Okay? Is this clear? Rho upon rho L into capital L. By putting FB's value here and then simplifying things. Okay, math step, I have skipped it, right? I didn't write it, I just did it on my mind. Okay, so now once we have this, right, once we have this relation, now we will talk about what happens when you displace it, right? So now if we displace it downwards, right, if we displace it little bit downwards, so we will take downwards positive. Be careful everyone, because we are displacing it downwards, we'll take downwards positive. Okay, so I'm drawing a new diagram here for the new case. So here this is the fluid level, and now the cylinder is this, but how much portion will be inside? It will be Y0 plus Y. Okay, so if I am saying that the downward displacement is Y. Okay, so earlier if like let's say 10 centimeter was inside, you push this inside by 1 centimeter, so now you will have 10 plus 1, that is 11 centimeter inside. Clear? So downward displacement is Y. So now what is the new buoyant force? What will be the new buoyant force? Can you tell me what will be the new buoyant force? Can you tell me what will be the new buoyant force? I'm waiting for your answer, everyone. Yes, it will be density of liquid into once again volume immersed, but this time do you realize that volume immersed has changed? right? It's not same as earlier. The volume involved has changed. Okay or not okay? Right? Basically this has come a little bit downwards, so more volume is inside water. So now try to recall the plan in all these kind of questions. What is our plan? It is that we think that there is some displacement y, then we draw FPD, okay, then we find the net force, and then after finding the net force we compare it with the I card of SHM. If it matches, very good, and then we try to find the force constant or torsional constant, and then we find time period, right? So these are the steps. So first of all, FPD in this position, okay, so it's very easy, of course, downward mg, no change in mass, so no change in mg, but now this is FB dash, okay. Again we have taken downwards positive. Why? Because we displaced this downward, we pushed it inside, so generally it's easier to take that side as positive, okay. So sigma f external using this FBD, okay, so it will be rho ALG minus FB dash, so that is rho small l into capital A into y0 g. I am opening this term. Did you understand that? I am opening this term. Clear? Okay, so now you see this looks like very complicated, but it's not. Use this relation that we have got. If you will use this relation that we have got here, right? If I use it in the second term, obviously there is no other scope, right? We just have to use it in the second term. What is y0? What is y0? Rho capital L into divided by rho small l. Okay? Into g, and then minus. So lots of things are cancelled, right? Here this cancelled with this, and then the same term here, isn't it? I hope you see first and second term are same. So that is subtracted, and finally you get minus rho l a into g into y. Do we get it like I card of SHM? Yes or no? Is the total external force proportional to the displacement? What's the displacement? Y is the displacement from mean position, right? So is the total external force proportional to y? Yes, you can see that here, because other things are constant. Rho l, a, g, they're all constants. Also, is it in opposite direction? Well, yes, because we said that displacement is downwards, but net force we are getting negative, that is upwards. Clear? So matches perfectly with simple harmonic motion. Clear? Understood everybody? Okay, once you do that, can you tell me what will be the force constant in this question here now? By comparing this equation with I card, compare this equation with the I card of simple harmonic motion. What will be K equal to by comparison? What will be K equal to? Yes, it will be obviously rho L A G. Clear? K will be equal to rho L A G. Sigma f external is equal to minus Ky. Very simple stuff. Okay. So K is rho L A G. Now if K is this, how much will be the time period? What the formula of time period of oscillations? Think, is this linear simple harmonic motion, that is translation, or rotation? Which kind of simple harmonic motion is it? And based on that, you have to write your formula here. Come on. What should be the formula? Yes, it will be d equal to 2 pi under root m by k, because this is translation, okay, not rotation. So put value of mass. Whose mass will this be? Whose mass will this be? Whose mass? Cylinder's mass. Very good. So if it is cylinder's mass, then use the data given in the question and put cylinder's mass over there. Right? So, what will be the cylinder's mass? Density into volume, of course. See, here we have done this so many times. This is mass, mg. So, rho, capital A, capital L, okay, that is mass. And divided by k, rho small l into A into g. So, what's cancelled? A cancelled, and this is your final answer. Hopefully, you understood this kind of situation as well. Right, where there is some object and it is in equilibrium. Obviously, if you don't do anything, it's just going to remain in equilibrium like this. So we found out that what will be y0, and then we see that if we push it downwards, if we tap it or if we dip it inside and release it, then it will start going up and down. So that is, there will be SHM. Right, that's what we have proved. Right, show that this will perform SHM. Yes, this is SHM. Clear? And then we found time. Alright then, so I believe we have talked about plenty of cases of physical situations or physical objects performing simple harmonic motion. Right? So again, don't forget that in any such question, you have a fixed pattern to solve it. Okay? The details inside may vary, but the plan is simple. First, mean position, you see whatever you have for mean position. Then you displace it a little bit. Okay, either rotate it or move it up, down, left, right, whichever way it is supposed to move. Okay, and then you draw its SPD again and then try to find out sigma f external. Right? If it matches with the I card value, then you have further steps to do. Right? So that's how you always do. Okay. Now let's go over to the next thing. Okay, so the next thing that we're going to learn is about phasor, about something called phasor. Okay. So what's a phasor? It's a new word for you, I understand. Okay, don't worry. Very simple to understand what a phasor is. Now this topic has also been given in your book. Listen to this carefully. This topic has been given in your book, but it is given in a slightly different manner. Right? But changing the title doesn't change content. Remember, in the book, they have written that we can consider the simple harmonic motion as component of uniform circular motion. Okay, this is the title given in the book. Simple harmonic motion as component of uniform circular motion. Right? But another way to get the same result is to use phasor. Okay, phasor method. Right? Why do I insist on phasor method? Because later on, when we go to some chapters of 12th standard, you need the phasor method. It's like a very simple, very quick way to get answers, right? Okay. But like I said, there's no difference between these two, remember. Let's start. First of all, I want you to remind of uniform circular motion. Uniform circular motion is where some particle moves in a circle, correct, with a constant speed. With a constant speed. speed v and with a constant angular speed, with a constant angular speed omega. Clear? Right? Hopefully you remember. And then the relation between v and omega is as follows: that if the radius of this circle is capital R, then v is equal to omega into capital R. Okay? Right? But instead of thinking of it in form of a circle of radius r, here we are going to say that suppose this is capital A. Suppose this is capital A. Alright? Suppose this is capital A. So instead of this, I get v equal to omega. Right? Again, watch it carefully. This is the speed. This is the speed of this particle. Okay? Let's name particles. Let's call this p. This is the speed of this particle p, which is going around in circle. Alright? This is clear. This is speed of p. Yes or no? Okay. Now, I am saying that we are going to take component of uniform circular motion. What does that mean? Or then I'll relate it with phasors as well. Don't worry. Okay, have you? Let's say that at some point of time, this particle p was not here. Let's say this is as usual x-axis with positive on right side, negative on left side, and y-axis. Okay? Right? So let's say that at a particular point of time t equal to, let's say at t equal to 0, initial, right? Obviously this is what is called initial. The particle was supposed over here. Let's call this position P0. What am I calling it? P0. Right? So do you realize that with the x-axis, it's going to make some angle here. Correct? The position vector of this particle from the origin will make some angle. Correct? Let's say that angle is phi 0. Let's say that angle is phi 0. Okay? Let's say the angle is phi 0. Obviously, you can take any angle, right? 30 degree, 40 degree, 65 degree, 79 degree, no problem. So at some point of time, let's say this angle is phi 0. Right. Now, do you realize that as this particle moves anti-clockwise, remember right now we are talking about a case where this moves anti-clockwise. Okay, I am saying that this particle p is going to move in anti-clockwise manner like this. Okay, right? What happens if it's clockwise? Worry about that later. First of all, it's important that you understand the simpler things. Then you try to use advanced scales. Okay, so if this particle moves anti-clockwise over this circle, right? Do you realize that this angle of the position vector? This angle of the position vector will gradually change, yes or no? The angle of the position vector will gradually change, yes or no? Well, now suppose, like I said, its angular speed is omega. Like I said, the angular speed is omega. So do you realize that at time t equal to t, that is from 0 to now t, the angle shall be phi 0 plus omega t. Yes or no? Is that clear? Why? Because this is displacement, angular displacement. Isn't it? If it's not clear, then I can go back a step and get it done. So here the angle is phi 0. Then here we have a question: how much is the angle? Because the angular speed is constant, I can use the relations of average. Right? Is this fine, everybody? Omega equal to delta theta upon delta t. So delta theta means final angle. Let's say phi. Let's say this is phi. minus initial angle divided by time interval. Hopefully this is clear to everybody that the final angle phi minus phi 0 equal to omega t, and that's why phi should be equal to omega t plus phi 0 or phi 0 plus omega t. Understood? Understood or not? Easy jatu ne? Get off tu. Well, so what we are saying is that after some time t, this position vector would have turned along with this, right? It may have gone anywhere, okay? The angles are just for representation, okay? I am not giving any particular value to the angle, right? So let's say after some time, the position vector becomes like this. This is not 90 degree again, okay? Let me just make it slightly different angle, otherwise you will get confused, right? So this is the final position, right? So do you realize that the angle was already phi 0 measured anti-clockwise from here, and now this has moved a more angle omega t. So total angle is now omega t plus phi 0. Is that clear? I repeat. Initially it was here at phi 0. It moved omega t angle and came here. Clear or not? It moved omega t and came here. So now the angle is omega t plus phi 0. Understood? Okay, so this is fine, everyone. Phi equal to omega t plus phi 0. Okay, now, what this means is that suppose I would, listen to this carefully now. Suppose now I would try to find the x coordinate and y coordinate in any situation, right? Let's say at some point of time when the angle is whatever. Suppose this is theta. Okay, we have done this in past. This is going to be very simple for you. Do you realize that this will be x coordinate, this will be y coordinate? Yes or no? Okay, so therefore we always know that y will be a sin theta and x will be a cos theta. Yes or no? Okay. So if we apply the same concept here, it is that at any point of time, okay, at any time t, okay, whatever it is, suppose this angle is phi, not phi 0. Phi 0 is for initial angle. Phi 0 is for initial angle, right? I hope you have seen that. But at any point of time t, suppose angle is phi, then do you realize that just like we are writing theta, we could also write it like this? Yes or no? And then by putting value of phi, we can get this. Understood the math? By putting value of phi, what is value of phi? Omega t plus phi 0. We can get this. Now what are we seeing here? Look at any one of the equations. Okay, even if you see both, no problem. But have a look at one first. What equal to a sin omega t plus phi 0. Do you realize that this is what SHM equations look like? Yes or no? Okay, so because we took the angle measured from here, the x-axis, so we're getting y equal to a sin omega t plus phi 0, right? Where this bracket is the angle. Again, don't forget. This bracket is an angle. Do you see that? The bracket is an angle phi, right? So what this means is, if you take uniform circular motion and then you take components of that. That is, you take x component, you take y component of the position vector, right? Like here we take this r vector is the position. If we take its two components, you can also say this is r vector, correct, position, and this is its y component, and this is its x component. So when you do that, we are getting both as SHM. So title clear, this one, this is understood, why it's given this kind of name. So what we have learned here is that you can think that SHM is just like a component. SHM is just like a component of uniform circular motion. Or you can think vice versa. You can think that uniform circular motion is made up of two simultaneous SHM. One is SHM in x-axis and the other one is SHM in y-axis. So when both of these independent simple harmonic motions are combined, what you are getting is uniform circular motion. Understood? Okay? Now, what about phasor? What's phasor here? Right? I will go on to that phasor because most of this is just the same idea, right? But I have to erase the whole board. So make sure you have written everything that you want. Shall I erase it? Okay, I'm going to erase it now. Fine. Frankly, we use the diagram here also because it's going to be the same diagram. I don't need to tell you anything more about it. Well, what's a phasor? First of all, let me explain. A phasor means rotating. Phasor means rotating vector. Phasor means rotating vector. Okay? So whenever we are seeing that there is some vector and it's rotating, okay, you could use this phasor method, okay, in any kind of concept, okay, not necessarily this topic, this chapter, any other thing. Okay. Phasor means a rotating vector. Where do you see a rotating vector? R vector. Don't you think? Can you imagine what will happen as this particle P moves around on circle? As this particle P moves around on circle, what will happen to its position vector? Will it rotate or not? Can you imagine, everyone? Think of it like the hand of clock. Okay? But yes, one distinction. Hand of clock turns clockwise. Right now we are talking about cases where this turns anti-clockwise. Is it fine? Okay, so it's just like that. This pointer, okay, like this. So it's a rotating vector kind of thing. Similarly, this one will rotate. Understood? Okay, now. So what does a phasor tell you about? See, first of all, phasor is where the name of this angle comes from. Whenever you write an equation, for example, here we got y equal to a sine omega t plus phi 0. Right? Okay, here we got this equation, y equal to a sine omega t plus phi 0. So this angle phi, which is omega t plus phi 0, is called phase angle. Okay, is called phase angle, right? Phase angle. Again, phase means referring to time. Okay, phase means referring to time. This phase of your life. When we say that, what does it mean? This part of your life. Okay. Okay, so just like that, phase refers to the time or the part of the cycle, right? So this is the phase angle, right? This is the phase angle phi, right? And initial phase angle. Now do you realize why we call this initial phase? What is the meaning of initial? T equal to 0. If you put t equal to 0, phi will become equal to phi 0. Is it fine? Clear or not? If you put t equal to 0, then phi will be phi 0. That's called initial phase angle. Understood everything so far about phase angle? Okay. So now, if we consider phasors that are rotating anticlockwise, listen to this carefully. If we consider phasors that are rotating anticlockwise, okay, so let's see. Time to draw new diagram. It's way too clumsy. See, here are the axes. Let's say this is that circle, right? Let's say this is the circle. So if a particle is rotating on the circle and you want to represent this, you want to use this to represent SHA, then do you realize you'll have to draw a position vector like this? What will be the length of this position vector? What will be the length? What will be the length of this position vector? Magnitude, alright. Radius, alright. One nothing. This is not unit circle. Okay. This will be A. The length will be A. Again, go back to what I told you. We are drawing a circle whose radius R. Instead of R, we are taking it as A. Why did we take it as A? Try to recall that triangle again. If we put angle phi here, this is Y, this is X, and this is A, isn't it? So now I will immediately get equation of SHA when A is amplitude, correct? Is it clear everyone that this length has to be A? Right? It is of course a radius. I am not saying it's not the radius, but amplitude is better. So now, if this angle is phi at some point of time, now I want you to imagine this thing, okay? It will be slightly easier for math students. You have done this earlier in your trigonometry class. So, as this will turn, the angle will change, yes or no? As this will turn, the angle will change. Correct? So, do you realize, listen to this carefully, do you realize that as this turns, okay, starting from this point, let's say, then one oscillation will be completed when this comes back to the same point, yes or no? One cycle, one oscillation will be completed when this comes back to the same point. Clear? You know, along with this, you can imagine what would happen to the particle or the component on the y-axis. Let's say that here we have a particle which follows this on y-axis. Okay, as this moves, this will move on y-axis. So it's like the component on y-axis. Do you realize that? Okay, now this is time for imagining. People, everyone. Do you realize that as this comes here, this particle Py will go up. This particle Py will go up. Yes or no? Both will meet here. Correct? Then what will happen? Then P will go down like this. Okay? It will turn. So as P goes down, Py will also go down. Correct? After some time, both will be here. That is T will be here and Py will be here. Does this make sense to you? Okay, what will happen after that? What will happen after that? This will travel further. Let's say it moves like this till here. So in that time, the y component of this P will start moving down till here, and once again they will meet over here. They will meet over here at this point. Okay. What next? this particle P will now go around the circle over here. And when that happens, this Py will start going up. So do you realize that as P goes around in a circle, okay, as P goes around in a circle, Py will move up and down in simple harmonic motion. Why do I know it is simple harmonic motion? Because its equation follows this pattern. Right? Did you understand what I am saying? As P goes around in a circle, as P goes around in a circle, Py will go up and down in simple harmonic motion. Okay? Same thing you can do for x also. Remember, suppose I take its x component. Then x will go left and right. Did you understand? As this goes right side, left side, it will go towards the left side. Okay, following it like this, here. Okay, then over here. You see, this is going left and right. Okay, then again left side. You understand what I am doing? Okay? So that's how it's going to move. That's how it's going to move. Now, so the phase angle again tells you how much has been or how much of the cycle has been completed. Phase angle tells you how much of the cycle has been completed. Have a look at this now. Okay, you can draw new diagram. Remember, the more diagrams you draw, the more you will understand. Suppose we have this circle. This is the phasor which is indicating position. This length is A and here. Right? This angle, let's say, is pi by 4. Suppose pi by 4, that is 45 degrees. So what this means is that it's already over here. Right? It's not starting at, think of y. It's not starting at y equal to a. Do you realize that this point is y equal to a, this point is y equal to minus a, this point is y equal to 0. Right? So it's not starting at y equal to a, it's starting somewhere in between. In fact, it's starting at y equal to a by root 2. Y by root 2 sine pi by 4 is 1 by root 2. Okay? So now as this moves, this particle will go up and down. Remember, we are only taking y component. So you can say that here this is halfway. Listen to this carefully. This is halfway between 0 and a. Not in distance. Listen to this carefully. This is halfway, this phasor is halfway between 0 and a. Clear or not? But in angle, this is where angle is 0, this is where angle is pi by 2, so this is halfway. Clear or not? Is this understanding clear? What I am saying is that this is halfway in angle, not halfway in the distance. This is 0, this is a, this is not a by 2. Again, it is a by 2, it's half in the angle. Clear? So like this, what you can decide is how much time it's going to take. For example, from here, listen to this carefully, from this position, let's say it wants to go here, then do you realize that one complete circle will take time period? Listen to this carefully. One complete circle will take time period. 1/4 quarter, that is, no, take the circle, take 1/4, means quarter, will take time t by 4, correct? But going from here to here will take half of this time. Do you realize why half of this time? Again, like I said, this angle equal, pi by 4, pi by 2. So it tells you that going from a by root 2 to a, tells you that going from a by root 2 to a takes how much time? T by 8. Why T by 8? Again, let's see it stepwise. Complete oscillation, one complete cycle, one circle for this phasor, one rotation, takes time period T. 1 quarter, so upon 4. Okay, and then half of that again, so like this. Did you understand? Right? So let's try one more. Okay, let's try one more. So suppose I draw a diagram over here and then you tell me how much time it's going to take. So let's say initially the phasor was here. Okay, this is the phasor. Right? I am marking I for initial. Okay, this is A and this is initial. So how much time will it take to go from here to here for this phasor? Let's say it rotates clockwise. Sorry, anti-clockwise. How much time will it take for the phasor to go from here to here? Very good. T by 2. That's right. Simple. Again, complete rotation of this phasor takes how much time? T. But here you have to go from this to this. That is, it's rotated by 180 degrees. Correct? Not 360. So it should take half the time. Did you understand? It should take half the time. Right? So you know what this is telling us? Listen to this. If you convert this, if you convert it to SHA, what this is telling you is that when this is here, you have y equal to 0. Y, so angle is 0. So y equal to a sine phi, but phi is 0. And y equal to a sine pi. Second time it's over here, pi, 180 degrees. So once again 0. So what this is telling you is that when some particle is doing SHA between y equal to plus a and y equal to minus a, then to go from 0 and back to 0, right? To go from 0 to a and then back to 0 takes how much time? T by 2. Clear? That you already know. I'm sure you realize that. Here to here T by 4 and back T by 4. So how much time? T by 2. Okay? So hopefully you related it with what we have learned earlier. Right? Next time we will solve questions related to this thing. Alright? Goodbye everyone.